In this scenario, we construct arbitrary non-convex safe sets and demonstrate safe control. A GP prior is placed on a candidate safety function, which we call as the Gaussian control barrier function. We see three different safe sets synthesized using the Gaussian CBF. In each experiment, random locations in the position state space are marked as safe or unsafe. Gaussian CBF synthesizes the safe set based on this data using its posterior mean and variance, giving high safety guarantees. A quadratic program is set up which uses Lie derivatives of the Gaussian CBF to generate safe control input. The quadrotor remains inside these safe sets, verifying forward invariance property. In this scenario, Gaussian CBFs are used to construct the safe set online. The quadrotor begins in an initial safe set. It collects the data in the form of states as inputs to the GP and distance to the obstacles as safety sample targets. The Gaussian CBF comprises of the GP posterior mean and variance, denoting the idea of safety belief and uncertainty respectively. We see in the experiment that unexplored regions have a high safety uncertainty due to the lack of data in those regions. As the quadrotor gets closer to the obstacles, it learns of unsafe regions in the state space. Notice that the safe set can expand arbitrarily in a non-convex fashion, since it is completely characterized in a non-parametric manner and relies only on the data. The quadrotor always remains in the safe set constructed by the Gaussian CBF and also does not collide with any of the obstacles. The obstacles are in the zero sublevel sets of the state space. In this scenario, we compare a standard CBF to a Gaussian CBF in the presence of noisy position states. The safety objective here is to remain inside a circle whose zero level set is shown. On the left, we see that the quadrotor goes outside the safe set using a regular CBF, since it does not have a way of handling measurement noise in position state. On the right, the quadrotor remains inside the safety boundary using Gaussian CBF. Gaussian CBFs can incorporate noisy inputs in its posterior prediction. This results in a more conservative safe set. Now, we see the effect of increasing measurement noise further. For the regular CBF, the quadrotor goes further outside the original safety boundary. On the other hand, Gaussian CBF results in a more conservative safe set due to the high measurement noise in the input, thus upholding the original safety boundary requirement of remaining inside the circle.